first of all between temperature and heat. So we're going to look at that and absolute zero. And then also there's two different new definitions actually for different substances, which we'll look at in a second. So first of all, we're going to look at what's the difference between temperature and heat. Now the most common misconception here is that heat is temperature. Okay, so if you have more heat, then that must be the temperature of the object. And they're not actually the same thing. They affect one another directly, but they're not the same thing. Alright? So an easy way to think about this is which has more heat? A kettle full of boiling water or a cup full of boiling water? So heat is specifically thermal energy, the amount of thermal energy that is stored in a system or a substance. So if I have a kettle full of boiling water and a cup full of boiling water, then they're both boiling, they're both water, but a kettle has a lot more. So the kettle has a lot more boiling water than a cup, therefore in total there is a lot more thermal energy stored. Okay, that thermal energy store of a kettle full of hot water, boiling water, will last me a lot longer than a cup full. So it's about the amount of thermal energy. There's more water in a kettle full, so there's more thermal energy stored. But the temperature of boiling water, as we know, is 100 degrees Celsius. So if water is boiling in the kettle, it's at 100 degrees Celsius. If the water is boiling in the cup, it must also be at 100 degrees Celsius. So the temperatures are the same. So that is not a measure of the amount of thermal energy or heat energy. Okay? Temperature is actually a measure of the kinetic energy of the particles in that system. So kinetic energy, all the way back in chapter 3, is the energy of an object moving based on the mass and the velocity of that object. So if the particles in a substance are moving faster for the same mass, because a particle has the same mass no matter what, then the kinetic energy that that particle has is greater. If it has a greater kinetic energy, it has a greater temperature. Temperature is specifically the amount of kinetic energy a substance has, the particles themselves, on average have. Okay? So boiling water is 100 degrees Celsius, it's a specific value of kinetic energy. 100 degrees Celsius, boiling water in a cup of water, same kinetic energy. But there's more particles in a kettle full, so there's more thermal energy overall. So the temperature is kinetic energy, which does transfer and translate to the amount of thermal energy there is. So the higher the temperature, generally, the more thermal energy you will have stored. But if you have two substances at the same temperature with the same kinetic energy, but you have more of one of them, then there's going to be a total more thermal energy. So you have more at the same temperature, you have more thermal energy. So that's just an amount of thermal energy stored in the substance. Temperature, kinetic energy, heat is thermal energy stored. Alright, so it's more about the amount we have in total. Now if we look at temperature a little bit more closely, we've just said that boiling point of water is 100 degrees Celsius. So most people know that water will boil and become steam or evaporate at 100 degrees Celsius. We know that water will freeze to become ice at 0 degrees Celsius. Now what is that? We said that degrees Celsius temperature is a measure of kinetic energy. So therefore are we saying at 0 degrees Celsius there is zero kinetic energy in the particles? That means if there's no kinetic energy, they're not moving. But can you go less than 0 degrees Celsius? Yes, you can. We know there are negative temperatures, negative 5 degrees Celsius, very cold, snowy, potentially place, icy place. So how is 0 degrees Celsius zero kinetic energy, zero temperature? It's not. Because we can go lower than 0 degrees Celsius, that means at 0 degrees Celsius, there is still some kinetic energy, it still has temperature. You keep going down the negative values all the way into the minus. The lowest temperature that we have on record, that we know is possible, the lowest degrees Celsius temperature is minus 273 degrees Celsius, point whatever, okay, 0.15. So the lowest temperature in degrees Celsius is minus 273. That means there is no kinetic energy in these particles at minus 273. So why doesn't the temperature scale start there? Well, the reason is it's a different temperature scale. The true temperature scale, the zero, lowest temperature that you can have where there is no kinetic energy, no movement, no motion in the particles, at minus 273 degrees Celsius, is actually 0 Kelvin. So it's a new unit for temperature, it's absolute zero. Absolute zero is minus 273 degrees Celsius, but the unit for that temperature specifically is given in units of Kelvin. Alright, so Kelvin is the true temperature scale. If you want to start at no temperature, no kinetic energy, no movement whatsoever, then you're on the 0 Kelvin. But on the degrees Celsius, it's a different scale. 0 on the degrees Celsius is perfectly at freezing and melting point of water because it's something that we experience in our everyday lives. Melting and freezing of water is a very common thing. So we create a new scale of temperature which makes sense because we live and exist around 0 degrees, not too much higher than 40 degrees Celsius and not too much lower than, say, minus 20 in the coldest of cold places. But if we're in Kelvin, which starts all the way down at minus 273 degrees Celsius, 0 Kelvin, then we're existing and living every day in a 273 Kelvin environment. And the number then goes up to 253 and so on. And it's unnecessary. We create a new one that is balanced around the 0 degrees Celsius at 273 Kelvin, where water melts and freezes. Then it makes a lot more sense, it's easier to use. But the true temperature scale is in Kelvin, from 0 Kelvin at minus 273. 0 degrees Celsius is 273 Kelvin. There's no such thing as negative Kelvin. If you want to turn the temperature from degrees Celsius to Kelvin, then you add 273. So 0 degrees Celsius is plus 273 Kelvin. 20 degrees Celsius is 293. You add 273, 293. If you want to go from Kelvin to degrees Celsius, you subtract 273. So for example, 0 Kelvin, subtract 273 is minus 273 degrees Celsius. So degrees Celsius to Kelvin, plus 273, Kelvin to degrees Celsius, subtract 273. Alright, and that's the absolute 0 true temperature scale in Kelvin versus degrees Celsius. Now what we're going to look at next is we're going to introduce a new definition, a new property of different substances and materials. This property is specifically known as specific heat capacity. Alright, so it's specific heat capacity. The symbol is C, small c for capacity. And what this is, this introduction of this new definition is about the transfer of thermal energy to a substance or from a substance. The definition of specific heat capacity is the energy required, the thermal energy required to raise the temperature of 1 kilogram, and that is important, 1 kilogram of a substance by 1 degree Celsius. So it's the energy needed to change temperature. Specific heat capacity is about changing temperature. How much energy is required to change the temperature of just 1 kilogram of a substance by 1 degree Celsius. Water, for example. Water has a specific heat capacity of 4,200 joules per kilogram degrees Celsius. Which means that if I had 1 kilogram of water, if I wanted to heat that water up to by 1 degree Celsius, let's say it starts at 20 degrees, I want to take it to 21. 1 degree Celsius change of 1 kilogram of water would cost or take or require 4,200 joules of energy. That's the specific heat capacity per kilogram. Just like density was per unit volume, per meter cube, specific heat capacity is per kilogram. So we compare different substances per kilogram, so we know that in a fair environment, by the same amount, how much energy would these things require just to change their temperature by 1 degree Celsius. If it requires more energy to change 1 kilogram by 1 degree Celsius, let's say for water it's 4,200, but for gold it takes a lot more energy per kilogram, then that has a higher specific heat capacity and water has a lower. Alright? It works in the reverse way as well. So for example, you could say how much energy is released by this substance if the temperature drops by 1 degree Celsius for 1 kilogram. So it can be heated, or the heat can actually be transferred out and it can lose that thermal energy as well. So specific heat capacity, the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius, the units of which are in joules per kilogram degree Celsius, or joules per kilogram Kelvin. Because although the values of Kelvin and Celsius are different, the change in temperature of 1 degree Celsius is the same as the change in temperature of 1 Kelvin. So they're the same change, so the unit could be in degrees Celsius or joules per kilogram Kelvin. It's the same thing. One more definition to introduce before we look at the actual equations for them is specific latent heat. So we have specific heat capacity, now we're looking at specific latent heat. Now, best example of this, if you start with ice on a temperature time graph, start with ice at a negative value of degrees Celsius, where the x-axis should really be at 0. You start at a negative value of temperature for ice, so let's say we start at -5 degrees Celsius. And I add thermal energy to the ice, then obviously we know now that thermal energy directly corresponds to temperature. Now it's not the temperature, but it will increase the temperature. So the temperature of ice at -5, if I keep adding thermal energy, I keep heating up the ice, the temperature will rise because the kinetic energy of those particles will rise. So it will go from -5 and it will keep rising to 0 if I keep adding heat. Now what happens at 0, as we know now, is the melting point of ice, where ice from a solid becomes liquid water. At that temperature, if you kept adding thermal energy, you keep heating it, the temperature doesn't change. So what's happening here at 0 degrees is that the ice is melting, it's undergoing a state change. So the temperature is not changing from 0 while that ice is undergoing the state change and becoming water. So where's my energy going? If I keep inputting thermal energy to the ice, why is the temperature not rising? So something is happening at the state change which is not going towards the temperature increase, but the energy must be going somewhere else. Now in the very start of 14a we said that solids are fixed in a regular arrangement with strong bonds between them. So what's happening in this physical change, this state change of melting from ice to water, is actually the bonds that are holding those solids together require energy in order to break the bonds. So in order to make an ice from solid to liquid, you must break or weaken those chemical bonds between them, and the only way to do that is to provide energy. So the thermal energy that goes into a substance at a state change, so at 0 degrees Celsius where the state is changing, is going into breaking the bonds. Now we create a new definition called the specific latent heat, which means how much energy would it take to change the state of 1 kilogram of a substance. So for example, if it's water, the specific latent heat of water could be, I'm making this value up because I don't have it in front of me, let's say it's 2,000 joules per kilogram. That means the latent heat of melting as well, it can be fusing or melting or condensing, so at different states there's different requirements, different energy needed. But if I say water is 2,000 joules per kilogram latent heat of melting, then what that means is 2,000 joules would be required to melt 1 kilogram of water, ice to water, or 2,000 joules is required to change the state of 1 kilogram of water. So specific heat capacity is how much energy is required to change the temperature of 1 kilogram by 1 degree Celsius. Specific latent heat is how much energy is required to change the state of 1 kilogram, units of which are joules per kilogram. So specific heat capacity C, specific latent heat capital L, two different definitions. Specific heat capacity is all about temperature changing, specific latent heat is all about the state changing. No change in temperature at a state change on the graph, it increases in temperature, it stops at 0, so it's horizontal. While it's melting, it's undergoing a state change. The temperature then goes up. When I've got water, all the ice is melted. My water now, if I keep adding thermal energy, increases temperature until it gets to the next temperature, which is 100 degrees Celsius, which we know is the boiling point of water. And then the water starts becoming a gas, starts evaporating and boiling at 100. So it's flat, horizontal line again. No change in temperature because the energy is going into changing the state, so breaking those bonds down again. And then gas, if you had the gas contained and you kept adding thermal energy to it, the temperature would rise again. So it's specific heat capacity for a temperature change, specific latent heat at a state change. Okay? And that's it for 14b, the two different definitions